All right. So we were talking about sampling last time. So we had this whole problem where we were trying to estimate what the voting outcome would be among a population of people, and we thought, okay, we're not going to ask everyone what their vote's going to be, but we're going to sample. We're going to sample some small number of people, and we hope that if we get an estimate of the voting patterns from the small number of people we do sample, that'll give us an idea of what the voting patterns are going to be in the overall population. And sampling, of course, is probably the most fundamental concepts in statistics, and of course, it's a fundamental concept in randomized algorithms as well. Almost all the time, you're going to be doing some kind of sampling, and you're going to infer something about the data you're sampling from just by looking at the sample. And of course, if you are thinking about problems in big data or what have you, this is a necessary tool. You actually cannot look through terabytes of things or petabytes of things, so you sample, and you hope that with a reasonable enough sample, you can get what you want. And what's going to be surprising is that a lot of the statements we will make about the errors of the samples have very little to do with the actual size of the data and have much more to do with the size of the sample. Which is very interesting because it basically says that I don't need to know, for example, in this case, as we will see, how many people there are in the population. All I need to know to control error of a certain kind is how many people there are in my sample. And that is very helpful for the things we're going to be looking at. So concretely, we said, okay, let's just take a sample. Let's figure out, can we say anything about what the sample values of N0 and N1, the people who vote 0, the people who vote 1, look like with respect to the numbers in the actual population? So we said, okay, let's focus on N1. And we can ask what the expected value of N1 is. It's a random variable. Every time I sample, I'm going to get a different value for N1. So it's a random variable, and therefore it has an expectation. And we can try to compute its expectation. So we said that we'll define N1 as a sum of indicator variables. Indicator variables are variables that are either 1 or 0. In this case, N1 was a sum of xi, where xi is 1 if the ith person we sampled votes 1, and if not, votes 0. And we made this crucial observation that expectation is a linear function, which means that to compute the expected value of a sum of things, it's sufficient to compute the sum of the expected values of the things. This is a trick we will use over and over and over again, which also means that whenever you want to state some problem, the trick is to express it in terms of a sum of random variables, because the expectations are easy to compute. You can't, for example, do the same thing for a product. The expected value of xy is not the expected value of x times the expected value of y, unless certain other conditions hold on x and y. But no matter what you know or don't know about x's, this will always be true. The x's, for example, don't have to be independent of each other. This will still remain true. Okay. So now, why this is nice is because the expected value of an indicator variable is very simple. Because of the way you write this down, it's very clear that the expected value of an indicator variable is merely the probability that it's 1. So we'll call that P1. And so then we did this continued the analysis, and then we observed that P1 was the probability that something would be set to, that a sampled person would vote 1, which is merely the fraction of 1s in the original population, right? And so the expected value of the number of people voting 1 in the sample is what you'd expect, is the number of people who would vote 1 in the fraction of people who would vote 1 in the actual population scaled appropriately. Right? Another way to say this is that it's basically just the number of people times the fraction that you're using. So this is what you'd expect, right? It's expectation, but it's also a reasonable outcome. That thing sort of scaled out in proportion. If I have a population size 100 and 40 people are going to vote yes, vote 1, then I take a sample of size 10, I expect 4 people to vote for. That's kind of what I expect. But because it's a random variable, the expectation is only what it looks like on average. On any particular trial, it's not going to be the expected value. It's going to be something else. If I toss a coin 10 times, I expect, well, the expectation is that of this random variable is that there will be 5 heads. But in any actual set of 10 trials, I might see 7 heads or 3 heads or 2 heads or 1. And so that's the next question we have to ask ourselves. If we're using a randomized algorithm, it's one thing to say, well, on average, it behaves okay. And what you really want to know is, how often does it not behave okay? And I drew these 3 pictures for you to show you different cases where things might behave or not behave okay. This is a case where everything is very concentrated close to the mean, so nothing really happens outside the mean. That's a case that's almost deterministic. This is a case where it's getting slightly worse. There's still some spread around the mean. And this is the case where it's even worse, where there's even more spread around the mean. And the concept you have to compute to understand how the behavior of this random variable is what is called a tail inequality. In other words, estimating the size of these tails that are outside the mean or some reasonable distribution. The smaller those tails are, the more concentrated around the mean, the happier you are. And in particular, what we're going to look at today is ways of computing this. So again, the language of that problem, what is the probability that the value you get, in this case N1, deviates from what you expect it should be, expected value of n1 by more than some threshold. So you can think of t as your tolerance for error. You're willing to tolerate some error in your estimation, but you don't want too much error. And so the actual probability you get will most likely be a function of t and maybe some other things as well. And our goal today is to understand how to analyze these things. Okay? So in general, the general form of this is always going to look like, what is the probability that some random variable minus its expected value is greater than some threshold. This is always the form of what a tail bound looks like, or a tail inequality looks like. It's an inequality because we want to say something like, this is less than equal to something. That's what we'd like to say. So the probability of something deviating a lot from its expected value is not very much. Okay? So what is the first thing you can say? So there's a series of, again, a long sort of set of techniques that people have used to try and prove things. But the way to think about them is to say, with how little information about z, or in this case n1, can you prove anything at all? And as you throw in more and more information about your random variables, as might be expected, you'll be able to say more and more stronger things about this tail behaviorality. So let's start with sort of a very basic assumption. We don't know anything about the random variable. All we know is that it's non-negative. Which leads us to something called the Markov Inequality. So let's say we have a random variable. We have some random variable x, which is known to be non-negative. It's at least a So like think of the number of times the coin toss rolls heads. And what we want to know is, can we give some bound on the likelihood of this straying very far from its average value? So the random variable is non-negative. So it doesn't go below 0. This is important. Why? Because now we can think, okay, suppose it could get a lot bigger than its average value. Right? Suppose average value was 5 and it could get to 100. Well, if it could get to the value 100 with some probability, that's going to affect the average value. Because the average is merely the computation of probability of value times the actual value. So if the random variable can get to 100 with some probability, then its average will have a term, some probability times 100. If its value can get to 200, then the average will get to some probability times 200. So if the value can get very big, its average also has to get reasonably big. It sort of gets pulled higher and higher as the number gets bigger and bigger. Another way of saying this is that, at least intuitively, it seems reasonable that you should not be able to get too far away from the mean, or that the likelihood of getting too far away from the mean should be small. And you can formalize this by saying something like this. The probability that the random variable exceeds some constant a times the expected value must be less than 1 over a. If you don't like variables, just plug in a equal to 2. The probability that your random variable is more than twice the mean has to be less than. So again, intuitively, what we're saying is that if you get too big, that can't happen with great frequency, because if it did, then your mean would also get bigger. And in fact, that's basically how you prove this. Right? So what is the let's see. So what is the expected value of this quantity? So we can write that the expected value of a, right, is equal to the sum, the expected value x, sorry, sum over x equal to 0 to a. Well, let's see. I'm being very careless here because I'm using summations instead of integrals, which I should be using. So let's assume these variables are discrete for now. But I should be doing the right in the integration. I'm just going to do things slowly. Okay. First of all, I did mention something. The other assumption I have to make on x this is a strange notation, but basically it means the expected value should be finite. The variable you're computing the tail bound for should have a finite expected value. If it doesn't have a finite expected value, that means your mean is off to infinity. Then there's no point of looking for tails. Because no matter how tiny your probability is, the value, it can get to a value of infinity, and then your tail is going to be very large. Okay, so there's nothing you can say. So assume the mean, which is important because we can say that this quantity, even though it sums to infinity, is still bounded. Okay, it's not unbounded. So you can write in this form. This is just trivial. I just take, okay, look at the part below, look at the part above. Right?
Here the random variable is what actually?
Any random variable.
Here the random variable represents which quantity?
A random variable is a mapping from events to the reals, from the case integers.
Is it the probability of this length of the base? Here the random variable denotes what?
It's just an arbitrary random variable. It doesn't denote anything in particular. We will apply it in the context of our sampling problem in a second. But right now it's just an arbitrary random variable, which means it's an arbitrary mapping from events to numbers. If you want, you can think of it like the outcome of a die roll, or you can think of it like the number of times your coin toss becomes heads, or you can think of it like the number of times your prediction of the weather of it raining outside is correct. You can pick whatever you want. It is an arbitrary random variable.
Okay, so if it is arbitrary, then why it will not be always regular?
Because my random variable could be if an odd number of people walk into class today, my x is equal to -1. If an even number of people walk into class today, my x is equal to 1. This is a random variable. It is well defined and takes value -1 and 1. It is not a variable for which you can apply the Markov Inequality. I just gave you an example of a random variable where you cannot, where it's in fact not always non-zero. I can choose whatever I want for the values of the random variable. Remember, the random variable is a function. It's a function from events to values. I can choose the values to be whatever I want them to be for an arbitrary random variable. It just so happens in the case I described to you, it has negative values. For those kinds of random variables, I cannot apply the Markov Inequality. It has to be one for its positive, and you will see why in a second. Okay. Okay, so let's see. So notice that all these terms are positive because the random variable is only ranging from 0 to infinity, right? So let's see now. So let me see if I can do this on the fly. So what I want to say is, okay. So if you look at the second term of the summation, all those numbers there are more than AEX, right? So we can write this as is greater than or equal to plus right? Why? Because all the terms here, all the i's are more than a times e of x. So if you replace each of those terms merely by a times e of x, this number only goes down. But then at that point, they all come out common. All they're left is a summation of x equal to I from this to beyond, which is the definition of this expression. And again, to be careful here, I should probably do this. Just to, again, because I'm being lazy to just compare this. Right? So all I've done is some algebra. I broke up the expectation into two parts, and then I replaced one part by a simplified version of it. Okay? Notice that because this is all positive, I can rewrite this expression again as because again that term is all positive. There's only positive there. Notice that if I had to write the expectation over the range of values of x and x is thought to be negative, this would have negative stuff there as well. I could no longer claim this term was positive. But because I know that I only need to worry about x being positive, all of these numbers are positive, so this is positive, therefore this is correct. And that's it. Take both sides out common, you get 1 over a. This is greater than equal to problem x greater than, which is exactly the reverse of what I want. So the proof is quite straightforward, but the intuition of the proof is basically saying, as long as my variable cannot go negative, which in some sense would counteract its positive values, if it can't go negative, its positive values can't happen too often. The values where it gets too big. That whole probability of it getting reasonably big cannot be too much, because otherwise you'll get in trouble. It'll pull the mean too far. Okay? So does this make sense? So again, Markov's inequality is basically this thing right here. And so the key assumptions are that x is non-negative and the expected value is bounded. Notice that this does not even require that, say, your variance is bounded or other nice properties. We don't care about that. It's a very lightweight inequality. It's also a weak inequality, as we will see. It means that it doesn't really tell you as much as you'd like to say about a random variable, but it's something. And you can actually show that you can't make this inequality any better, that there exists a random variable for which this is in fact exactly what you would get. I mean, this looked very sloppy. I was just throwing out a bunch of terms like, oh, this is very equal to. If you look at this, you might think, well, maybe I could improve this relationship. It turns out you can't. This is the best you can get. You can construct a random variable where exactly this will happen. This will become an equality. It will be exactly 1 over 8. So the probability of being more than twice the mean is half. Probability of being more than 3 times the mean is 1/3. That's an easy thing to remember. If you're positive. If you're a positive random variable or non-negative random. Okay. How would this apply in our setting? How would this apply to us? It would say something like, if you remember, we had this variable. So we look at our setting here. We have the random variable n1, right? n1 by definition is positive. It's counting the number of votes for 1. So it's a positive random variable, so that's fine. The Markov inequality applies to it. We know the expected value of n1. The expected value of n1 was equal to the size of the sample times p, which was the probability of seeing a vote for 1 in the population. Right, so you can think of this as this m times n1. Remember, capital letters are for the population, small letters are for the samples. So what we're saying is that the probability that n1 is greater than 2np is less than or equal to half. By Markov inequality. Why? Because we just put the mean value there. The probability that the number random variable is more than twice the mean is less than half. So, okay, it's not bad, but it's not very good either. Because it doesn't tell you anything about, well, could sampling more things help me? And it's saying, like, I don't know, whatever you do, the probability that it's more than twice the mean is less than half. That is not helpful. It is not helpful because it does not say Suppose I took 1,000 samples, so I took 10,000 samples. Intuitively, if you think about this, the more samples I take, the more accurate I should get. In the limit, if I looked at the whole population, I should be perfect. I should never be more than n times p. It should be exactly n times p. And they're saying, nah, I don't know, you could still be more than 20. So the Markov inequality is weak. And that's sort of by necessity. The way it's set up is very weak. It's not exploiting properties of the random variable that we want to exploit. And that leads us to ask, is there any other tool we could use to analyze the same process to get a better bound? So again, I want to emphasize, I'm not going to change the sampling procedure. Okay, that's going to remain the same. All I'm going to do is say, is there more information on how I do the sampling that I can exploit to get a better bound? Okay? All right. And that brings us to the next thing. This is called Chebyshev's inequality. So once again, we had this idea that we wanted to capture the tail behavior of a random variable. We wanted to capture the probability that it deviates from its mean by a certain amount, or by a certain amount. Now we're going to assume a little bit more about the random variable. We're going to assume that it has what we call bounded variance. So again, just recall, if I have a random variable x, the variance of x is the expected value of its deviation from its mean squared. It's not the square of the expected value of the deviation, it's the expected value of the square of the deviation. Why are we doing that squaring? Well, we're saying, look, we don't care if the random variable deviates from mean from one side or the other. We just care about the magnitude of this, and then we square it. The standard deviation is the square root of the variance. So if you follow the standard deviation, which is why we often write this as, another way of saying. We're going to now produce a new inequality that exploits any knowledge you might have about not just the mean of the random variable, but of its variance. Okay. In particular, we're going to assume that the variance of the random variable is bounded. And this, by the way, is rare to find random variables whose mean is unbounded. It is much more common to find random variables whose variance is unbounded. If any of you have heard of something called a heavy-tailed distribution, which show up a lot in sort of a lot of data analysis problems, that heavy-tailed distribution is a distribution that doesn't sort of cut down nicely, kind of goes very slowly. And you can show that these kind of distributions, as a formal description of them, have unbounded variance, which makes life very, very difficult for dealing with them because things like this don't work. But for now, let's assume everything's good. So in particular, we will assume that we're given a random variable. So we're given random variable x such that the variance is bounded. By the way, if the variance is bounded, the mean will also be bounded. Let us apply the Markov inequality. So I'm going to derive the Chebyshev's inequality for you by applying the Markov inequality to our auxiliary random variable. So let's watch this. So let's define y is equal to x minus e of x whole square. X is a random variable, again an arbitrary random variable. Therefore y is a random variable. What can we say about y? Well, first of all, good, squares. Also, because we said the variance of x was bounded, and the expected value of y is precisely the variance of x by definition. Which means we can apply the Markov inequality to y. Right? So we can say something like the probability that y is greater than e of y times a is less than equal to 1/3. I mean, that's all well and good. In fact, just to make things convenient, I'm going to put a square, and you'll see why. It's the same thing, I just chose a different parameter relation. But now let's actually substitute our things back in. So what we're saying is that the probability that x minus the expected value of x whole squared is greater than a squared, the variance of x, is less than or equal to 1 over a squared. Right? Okay, but that's that inequality inside the probability. I can take the square root on both sides. So this becomes the probability that the absolute value of x minus its mean, because the square root of the square is the absolute value of the difference, is greater than a times its standard deviation. It's less than or equal to 1. And this is Chebyshev. So I want to draw your attention to two things. Especially this in relation to the Markov inequality. Let me see if there's a way I can put them on the same page. A little tough. Okay. Let me first draw your attention here. Here we said that the probability that you deviate from the mean, and think of A as kind of a unit of mean, right? The probability of deviating from the mean in units of A, measured away from the mean, is 1 over A. So as you get further away from the mean, the probability of this event happening goes down, and it goes down roughly at the rate of 1 over A. So it's like a reciprocal. Okay? All right, keep that in mind. If we now go to the Chebyshev inequality, we're saying the probability that you deviate from the mean, measured in units of the standard deviation, goes down as 1 over a squared. It goes down faster. In other words, if your variable has some kind of variance, then measured in units of that standard deviation, square root of the variance, the rate at which the probability of it exceeding the mean by that much goes down by a quadratic factor rather than a linear factor. It's going down faster. Which means your distribution, instead of looking like this, starts looking like this. Because things are dropping faster. And as we saw earlier, that's a good thing. Because you want these tails to be small. So we're saying the probability of deviating from the mean is actually smaller than we thought it was if we measure it the right way and exploit the fact that our random variable may have bounded variance. Any questions about this? Yeah.
No, maybe I can scroll the next. Can you explain quickly how you got from the red box step from previous to the red box?
Right.
Just out.
So I am looking. So I proved that the probability of x minus e of x squared greater than a squared bar x is less than or equal to 1 over a squared by the Markov inequality. That was a straight application. Then I merely said, look, this is an event. This event is being expressed as an inequality. I could take the square root of both sides of the equality. It's the same event. I'm just rewriting mathematically what it says. Instead of saying this is more than that, I'm saying square root of this is more than square root of that. And that gives me this. So this works better if you have a bound on sigma b. If you don't, of course, you can't use it. But let's apply it to Markov. So again, we had the sampling problem, right? And we had this random variable f1. And essentially, in order to do anything with the Chebyshev inequality, yeah, did a question?
Then why do we have to have a bound on sigma?
Sorry?
Where is that we have to have a bound on sigma?
Recall that I applied the Markov inequality to this auxiliary random variable y. The condition to the Markov inequality is that the variable should be non-zero, positive, non-negative, sorry, and its mean should be bounded. But the mean of y is the variance of x. And that's it. Okay. Alright. So, how does this apply to us? The central question we're going to ask ourselves is this. If you think of filling the blanks, well, x is our n1. Expected value of x we already figured out. We just don't know what sigma of x is. What's a variance of x? So that's of our random variable. So we have this again, this random variable n1, and what we need to figure out is what is variance of n1. Now again, as before, we can write n1 as summation of xi, and so the variance of n1 is equal to the variance of the summation of xi. Now unfortunately, the variance of a sum of random variables is not the sum of the variances in general, because you could have variables that correlate with each other. And if you think of how, if you take a square of things, you get these cross terms, and you look at how cross terms correlate. But there is one case when, in fact, the variance of the sum is the sum of the variance, is if the variables are all independent. In other words, if x1 and x2 are independent random variables, then the variance of x1 plus x2 is equal to the variance of x1 plus the variance of x2. And the way you prove this is basically by remembering that if two variables are independent, the probability of x1 times the probability of x1 x2 is equal to the probability of x1 times the probability of x2. And you just plug that into the definition of variance, and you can just work this whole thing out. It all factors out. Notice how I said we did our sampling. If you recall from last lecture, I said we sample with replacement. That means after we sample someone and ask them for what they're going to vote for, we might ask them again. We ignore the fact that we asked them earlier. Which means every time we make a choice of who to ask, that choice is independent of all the other choices we made. This is like as if we start all over again. We retconned our entire sampling and start each time. If we ask someone what their vote was and never talk to them again, then the next sample is somewhat dependent on what happened now. And we can no longer do this analysis. So it is often convenient to assume we sample the replacement even if it seems wasteful, because our estimates are easier to analyze. And there are some general theorems saying, under what conditions sampling with replacement looks more or less like sampling without replacement. There's a nice sort of theory around that. But for now, fortunately, because we have independence, our variables are independent of each other, we can actually replace that variance of the sum by the sum of the variances. So this will be equal to okay? All right. Well, what's the variance of a single indicator random variable? Well, we have a random variable xi. We know it's 1 with probability p. It's equal to 0 with probability 1 minus p. Okay? We know its expected value is p. So its variance, by definition, is the expected value right? Which is equal to the probability that x equal to 1 times 1 minus p squared plus the probability that x equal to 0 times 0 minus p squared. This is just the definition of expectation. This is equal to p times 1 minus p squared plus 1 minus p times p squared. Right? Okay. So if we simplify this expression, what do we get? We get p times 1 minus p times 1 minus p plus p, right? Which is equal to p times 1 minus p. Okay. All right. Now we substitute, we replace this, and so we remember we have to sum up all the variances. They're all the same random variable. They all behave the same way because they're independent of each other, and because they're independent and they're identically sampled from the population. So we now conclude that var of n1 is equal to n times p times 1 plus p. And if you ever done basic sort of statistics, this kind of form should be familiar to you. Bernoulli random variable. Okay, but we're not done yet. We still have to figure out what to do with all this. Right? So now let's plug this in. If you remember our Chebyshev inequality, it looked like this. Right? So let's plug this in and see what it looks like. So let's, there's another way to write this out, is to write this out in the following form. The probability that x minus the expected value of x is more than t is less than equal to sigma squared by t squared. It's not hard, or it's not hard to see why this is true. Just replace a sigma by t. And you just substitute this and you get exactly what you're looking for. Okay. So if you, let's see now. So if you plug this in, you get something like the probability that x minus np, or rather n1, is greater than t is less than equal to np times 1 minus p over t squared. Okay, we're not done yet. But we've got now something very interesting, because somehow n has made an appearance in our tail. Whereas before it was just, a fixed constant. Now we've got a little bit more handle over this. There's something to do with t and n. There's some interesting relationship here. So let's now go back to our original problem and ask for a little bit more information to help us figure out how to use this inequality. So if you recall, our goal was to figure out, who was likely to win the election, right, if you're voting, based on the sample. So we had those population numbers. We had n1 minus n0. And so we had n1 and we had n0. And of course, there's some gap between. So there's some gap. So let's say that n1 minus n0 is equal to some gap g. And so you can think of this as a fractional gap between the two in the population. Right? Let's say for now that n1 is the sort of the winning side, right? N1 is bigger and n1 is small, for argument's sake. And now we want to do this estimate. And what we want to make sure, you can read. So if you think about the gap between n1 and n0, what will happen is in your sample, in your sample now you can think of the expected gap. And you can show this. So it will be something like the expected gap will be something like n times g. So it's the same, it's the original gap sort of scaled down to this. And what you don't want is your estimate of the value to be more than half the gap. Because at that point, you might flip things around. If you have a fixed size sample, if the gap, so if you have, for example, so let's say concretely that let's say n1 was 0.6 times n, and n0 was 0.4 times n, right? So the gap here, g is equal to 0.2. Right? And what you don't want is the estimate to deviate from, so what you want is to say that you want to see the probability that n1 minus its expected value, right, is more than the gap divided by 2, or in particular 0.2 n divided by 2. Because if you cross that gap, that's when your sample result might look different from the global result. So this is the amount you want this to not deviate by. Okay? So let's look at this particular example here. Right? So in this case, what we're saying is that we want to know the probability that n1 minus the expected value of n1 is greater than 0.1n. In other words, P right? Okay. But we also know that P in this case, the probability of N1 is 0.6. So we can write this whole expression out as this probability by Chebyshev inequality is going to be less than or equal to N times 0.6 times 0.4 divided by 0.1N squared. If we simplify this again, which is equal to, what is this? This is 24 divided by N. So what we're saying now, which is a little bit more interesting, is that the probability that your estimated value of N1 deviates from its expected value is a number that decreases with N. Which means as small n, your sample size increases, the likelihood of this happening gets smaller and smaller and smaller. And this is exactly what you want. So now you can say, oh, you know, I want to make sure that in my sampling, my probability of error is less than 2%. Right? So what I'm saying is I want my probability of error of deviating from this by more than 0.1 to be less than 2%. So I want this number which means that n is equal to 24 times 100 over 2, which would be equal to 4. So as long as you take 1,200 samples of people and calculate their votes and look at the fractions, the chance of you making a mistake on deciding who won is going to be less than 2%. And this has nothing to do with the population size. Of course, what it does have to do is with the closeness of the race, right? In particular, we said there should be gap over 2, right? So if we put that down there, if we wrote this out differently, we'd say that the probability that N1 minus E of N1, right, is less than gap over 2 is less than or equal to n times 0.6 times 0.4 divided by gap over 2 squared. Another way of interpreting this is saying that if the gap between the two sides, the N1 and N0, is very small, it's like 51% to 49%, it's a very close race. What does this mean? This means you need to sample more in order to get the desired probability points. Because the smaller the gap gets, the bigger this probability gets, the worse your news gets. Remember, you want this number to be very small. If the gap gets small, this number gets big. You don't want that. So what this is saying two things. It's saying if you take more samples, you will get a better estimate. But if the thing you're trying to estimate is very, very close, then you need more samples to get it. So in a close election, you need more samples. And this is again intuitively reasonable, right? If you have an election that can turn on 1%, and your margin of error is 3%, you have no idea what's going to happen. You have a much tighter margin of error. So the result of applying the Chebyshev inequality tells you all kinds of things about how to design your sampling process. And that's why the tail bound is important. It basically says, look, this is the relationship between the number of samples you're going to use and the probability of error you're going to get. You pick what you want. I will tell you what the result is going to be. You want this error, you need the sample. You pick the sample size, this will be your error. If you ever look at sort of like medical studies where they do power calculations, these are the kinds of things they're doing. They're saying, look, if I have these many patients and I run this test and I get the result, this is the likelihood of this outcome being reasonable. There's all kinds of tests. They're phrased differently in terms of null hypothesis, but basically they're doing the same thing. Okay. So this is the power of these kinds of inequalities. The Markov inequality didn't really give us much. It gave us some very rough idea, okay, fine, yeah, you'll get used. But from the Chebyshev onwards, you start getting a concrete quantitative bound on the number of samples needed to get a certain point. Okay. And one question you might be asking yourself is, well, I did this trick with the variance. What happens if I do this trick with higher moments? What happens if I take the x minus e of x cubed, or x minus e of x fourth? The answer is actually quite interesting. Just like how when we use the Chebyshev inequality, which use the variance, which is a second order moment, we get a decay which is 1 over t squared. Just like with Markov, which is using the mean, which is a first order moment, we got 1 over t. If you use higher order moments, you get even sharper moments. So this is great. Why are we wasting our time on this stupid Chebyshev? We should always use better moments. What's the catch?
You can only use even higher bounds, right?
No, you can use odd.
Because if you use odd higher bounds, it can become negative, and then
You can't prove it using the Markov inequality, but you can still derive a bound. But let's say even use even moments. What's the catch? Why can't I use like the 100 moments? What's the catch with this? Where would go? What in our analysis could potentially break? Huh? But what?
We bounded the variance there. We bound the
higher moment. And intuitively, if you're raising things to a higher power and summing up to infinity, the chance of it becoming unbounded is higher. So it is much harder to get a random variable that has bounded 4th order moments, or 10th order moments, or 20th order moments than it is to get a random variable that has bounded 2nd order moments. So you don't always have the luxury of going to higher order moments, but often you do. And in fact, for a lot of the random variables we look at, like the ones in sampling where you have Bernoulli random variables, all of their moments are bounded. All their different. Essentially, this is because think of the way we compute with variance. These are all very tiny numbers. It's something minus 1, right, basically. Something minus this. So all these numbers are less than 1. And so the higher powers only get smaller and smaller and smaller. So you never have a problem. Which means that if you have an appropriately chosen set of random variables, you can do, in fact, much better. In particular, a bound that I will only sketch out, I won't give you the full details of, but that has a wide-ranging sort of set of applications, is something called a Chernoff bound, or a Chernoff-Houghton bound, depending on which version of you use. This is like a family of bounds that say something like, roughly speaking, the probability that the deviation from the mean, right, is more than some small factor times the mean. Again, so you're a little bit away from the mean, is less than not 1 over delta squared, 1 over delta cubed, 1 over delta fourth. It's exponentially. So those tails, they drop off exponentially. And if you've seen distributions that have that kind of behavior, does it ring a bell? There's a very well-known distribution that has that kind of behavior. Normal distribution, Gaussian distribution. So what does a Gaussian distribution look like? The probability, what is it? Probability of x equal to something is proportional to e to the minus x minus mu squared over 2 sigma squared. This is sort of constant proportionality here. It decays exponentially with this distance from the mean. And this form is what is called a sort of essentially an exponential tail. That the tails drop off exponentially. If you can get a distribution or a behavior where tails drop off exponentially, this is really, really good. Because that means that the distribution doesn't look like this, it doesn't look like this, it looks, which means the tails are tiny. Which means the probability of being far away from the mean is really, really small. It's exponentially small, in fact. And that's sort of the gold standard for what you want with a randomized algorithm. That you can get an exponential tail. And often you will be able to get that kind of tail. Okay, there are various forms of this inequality. There's a whole book on basically Chernoff-like bounds. And there are different flavors depending on, again, different conditions you might put on x. Right? X has to have all its moments, but x usually is written as a sum of random variables, and they might have bounds, and so on and so forth. There's a whole variety of these things. So I'm not going to give you all of them right now, but we will start seeing applications of these bounds in some of the examples. But today the whole message was the study of tail bounds and tails on random variables gives us a way to bound the error of randomized algorithms, in this case, sampling. And we'll see this happen again. Okay? All right. I will see you all on Wednesday.